Hello everyone, this is Jia Baojing from Eastern China Normal University. It's my honor to present our work, Efficient Non-Learning Similar Subtrajectory Search. First of all, let me give you a quick overview of the background of our work. In recent years, the increasing popularity of mobile design has led to a significant surge in trajectory data. One of the major challenges in analyzing such data is to identify the trajectory that is almost similar to a given one. Among the vast pool of trajectories in the database, unfortunately, it's not always easy to ensure that two trajectories are of the same length or even closely related. To illustrate this point, let's consider the two measures shown in the slide: the data trajectory tau d and the curve trajectory tau q. When we look at the trajectories as a whole, they don't appear to be very similar. However, it turns out that tau q is actually similar to a specific portion of tau d. This is where the problem of similar subtrajectory search comes in. It involves finding the most similar portion of tau d for a given tau q. Similar subtrajectory search has numerous practical applications. By searching for similar trajectories in a database, we can estimate the travel time for a given query trajectory. Additionally, we can use trajectory queries to analyze the movement pattern of athletes on a sports field. The similar subtrajectory search problem still poses many challenges. Assuming the length of the query trajectory is m and that of the data trajectory is n, there will be n-squared subtrajectories for each data trajectory. Considering that the time complexity of dynamic program-based trajectory distance calculation is mn, brute forcing the optimal subtrajectory has a time complexity of mn squared. On the other hand, there are currently many distance functions available, making it difficult to find a universal approach that works well for most distance functions. Some existing work still has limitations in solving the problem of similar subtrajectory search. ExactS, for example, removes redundant calculations from brute force search and can compute accurate solutions in mn-squared time complexity. The author also proposed POS and PSS algorithms to obtain approximate solutions, as well as LRS and RLS skip algorithms based on reinforcement learning. On the other hand, some works has attempted to obtain accurate solutions in NM time complexity, but they are only applicable to specific distance functions such as DTW and FD. Compared to previous work, our algorithm is capable of achieving an exact solution with ONM time complexity for the vast margins of distance functions. What sets our work apart from previous approach is that we don't directly search for the optimal trajectory. Instead, we transform the problem into finding the optimal matching sequence. Each distance functions may have different costs associated with the same matching sequence. To address this, we provide iterative formulation for computation the optimal subtrajectory using dynamical programming for each distance function. Next, let's introduce some key concepts mentioned in this paper. We define a trajectory as a set of points, while a subtrajectory is a set of continuous points that forms a part of the trajectory. We use I to represent the starting position of a subtrajectory and J to represent its ending position. Moving on, we define the matching sequence between a query trajectory and a data trajectory. The matching sequence consists of a set of continuous integers in increasing orders, which means that if I is bigger than j, then ai must be less than or equal to aj. Moreover, ai equal to j implies that tau qi matches tau dj. Let's further illustrate the matching sequence using an example. The figure shows two different matching sequences for the same trajectory. The first matching sequence is 1, 1, 2, 2, 3, 3, 5, 6, 9, while the second matching sequence is 1, 1, 2, 4, 5, 6, 7, 8, 9. In both matching sequences, tau q4 is matched with different points. In the first matching sequence, tau q4 is matched with tau d2, while in the second matching sequence, tau q4 is matched with tau d4. Different matching sequences will have different conversion costs. Next, we provide the cost of converting a point in the query trajectory to a point in the data trajectory. Given a matching sequence, when ai equal to j, and we want to convert the point tau qi to the point tau dj in the data trajectory, there are three possibilities: deletion, substitution, and insertion. When ai sub 1 equal to j, we should delete tau qi. When ai sub 1 equal to j sub 1, we only need to replace tau qi with tau dj. When ai sub 1 equal to k, well, k is smaller than j sub 1, we need to substitute tau qi with tau dj and at the same time insert tau dk at 1j. For any given matching sequence, we can compute the conversion cost of transforming the query trajectory through the defined matching sequence into a subtrajectory in the data trajectory. Since the matching sequence only considers a subtrajectory of the data trajectory, we need to consider an additional prefix subtrajectory and the suffix subtrajectory. We define the distance between the two trajectories as the minimal sum of the conversion cost for all corresponding matching sequences, along with the cost of inserting the prefix and suffix subtrajectories. As we are studying the problem of similar subtrajectory search, we adopt an asymmetric approach in designing distance functions. However, we also prove in the paper that our defined general distance functions can specialize to the measure of the distance functions. After introducing the above concepts, let's briefly explain the idea behind the CMA algorithms proposed in this paper. We have proved two theories. The first theory states that the optimal matching for the optimal subtrajectory of the data trajectory must not include any prefix or suffix subtrajectory, and the second theory states that the optimal matching for the optimal subtrajectory is also the optimal matching for all subtrajectories. By proving these two theories, we can transfer the problem of searching for the optimal subtrajectory into the problem of finding the optimal matching. To solve the problem of finding the optimal subtrajectory matching, we introduce a concept called optimal partition matching conversion cost, C. Cij denotes the minimal cost of converting tau qij into a subtrajectory of tau dij. When tau qi matches tau dj, we can use dynamical programming to compute Cij. The example in the figure illustrates the computation process of Cij, where Cij is the minimal value obtained from these three cases. We can prove that the distance between the optimal trajectory of the query trajectory and the data trajectory can be calculated using Cij. Since the time complexity of computing Cij using dynamical programming is 1, we can compute the optimal trajectory in ONM time complexity for given values of n and m. We provide the calculation expression for Cij using the WED as an example. We provide an example to demonstrate the calculation process of Cij. C48 can be obtained by inserting tau D7 and replacing tau Q4 with tau D8. Based on C36. The insertion cost is obviously smaller than deleting tau Q4 or directly replacing tau Q4 with tau D8. Similarly, C698 is computed from C58, which means we need to delete the tau Q6. Finally, we conduct extension experiment to validate the calculability of the proposed algorithms in this paper. We use 3 datasets with different trajectory lengths in our experiments. We use the evaluation metrics AR, MR, RR, and distance, which were used in previous work to compare the quality of the optimal trajectory found by different algorithms. The table shows the result of different algorithms by subtrajectory found by approximate algorithms when using DTW as the distance functions is far from the optimal subtrajectory. In addition, the subtrajectories found by the RLS and the RLS skip algorithms learned based on reinforcement learning are also far from the optimal subtrajectories. CMA can find the exact optimal solutions in all cases. Compared with exact as the efficiency of CMA has improved nearly 200 times on Xi'an datasets and nearly 15 times on the Portal dataset. The longer the length of the trajectory, the more the improvement of CMA over exact S. CMA can find the optimal subtrajectory related quickly regardless of the distance functions. POS and PLS skip are the fast, but they are approximate algorithms. All algorithms except CMA has poor performance when DTW is used as the distance functions, regardless of the length of the query trajectory. It is because that DTW allows different points in query trajectory matches the same point in the data trajectory. Furthermore, the effectiveness of the approximation algorithms is improved as the length of the query trajectory increases when EDR is used as the distance function. The algorithms proposed in this paper can be applied not only to trajectory represented by GPS points, but also to trajectories represented by other forms such as points or edges on the network. As the length of the query trajectory increases, the time required to find the optimal similar subtrajectory also increases, and the distance between the optimal solution and the query trajectory also to increase. The figure shows that the time to find the optimal solutions increases linearly with the length of the data trajectory for all algorithms. We also observe that longer trajectory lengths make it easier for approximation solution to find better solutions. That's all my presentation. Thank you.